Good morning, everybody. I am very disappointed in the news that we received yesterday from Governor Beshear. I understand the reasoning behind it, but I was really kind of holding out hope that I would get to see you guys again very soon. We are going to really be pushing hard to complete our course on time. There is a distinct possibility that we will go beyond May the 8th. I just want to prepare you guys for that in advance. I'm waiting to hear back from the board and also talk with EKU about how we're going to proceed to make sure that we cover all the content for this class. This third unit only has 8 sets of notes in it. We are on set 2 today, so that means our test will probably be one day towards the end of next week. What we're looking at today is the critical value approach to hypothesis testing. And this is computationally, it's nothing that you've not seen before. It's just we're kind of taking some of the things that we've been doing, we're going to tie them together, and we're going to test these hypothesis tests that we're coming up with. So remember, with a hypothesis test, you have a null hypothesis and an alternative hypothesis. And we are looking for what we're going to call a cutoff point or points based off of a z-score determined by the significance level of the hypothesis test. And we're going to just jump in here and look at an example real quick. But before we do that, let me kind of clarify where we're going with this when we talk about the z-scores. So we have 3 different types of hypothesis tests. We have the two-tailed test, where we use the not equal to in the alternative hypothesis. And if we think about that in terms of the normal curve, we're going to generate 2 z-scores, and we're going to have these rejection regions that lie to the left or to the right of those z-scores. We accept the null hypothesis if it falls anywhere in between those 2 z-scores. The left-tailed test is when we use the less than symbol. And in terms of the normal table or normal curve, that would be we have a rejection region that lies to the left of some specified z-score. And then finally, with the right-tailed test, where we use greater than, we have our normal curve and we have some z-score. Anything that lies to the right, we reject the null hypothesis, and anything that lies to the left, we do not reject the null hypothesis. Keep in mind, we don't say we accept the alternative hypothesis. We are simply either rejecting or not rejecting the null hypothesis. So the first thing that we want to do is look at an example, and that'll kind of help clarify things. And what we're talking about here, I decided to pick on Jaron and Misty, is that Jaron tells Misty that his average drive of a golf ball is 275 yards. Misty, who also knows that Jaron has a propensity for exaggeration, is somewhat skeptical and asks for substantiation of his claim. So they go to the driving range and he hits 25 balls. Misty, being ever diligent, decides to record the length of each one of these drives, and she provided us with this fancy table. The sample mean of these 25 drives is 264 yards, 264.4. So this is our X bar. That's our sample mean. He still maintains, though, that on average he drives a golf ball 275 yards, and that this poor performance today could be attributed to just simple chance or the pressure being watched by Misty. Now, at the 5% significance level, so this is our alpha, is equal to 0.05. We've talked about this. We want to determine whether or not Misty's claim is more appropriate than Jaron's claim. And that is going to be part A, where we state the null and alternative hypotheses. So the null hypothesis is Jaron's claim, and the null hypothesis is that mu is equal to 275 yards. And remember, please, if you're given units, use your units in your answers. The alternative hypothesis is Misty's claim, and her claim is that mu is less than 275 yards. So based off the sample data, we're going to determine if there is a reason to accept Jaron's claim that his average drive is 275 yards, or reject the claim that his average drive is 275 yards. So part B says to discuss the logic of this test. And when we talk about discussing the logic of the test, we're just talking about why are we doing this? What are we looking for when we complete this test? And the test that we're looking at here is that if the null hypothesis is true, so if H naught is true, then mu does in fact equal 275 yards. So when we test this, we're going to say we have to determine if it's approximately equal to 275 yards. There can be variations in samples, but there has to be a tolerance that we would accept. For example, we may not accept a sample mean of 212 yards as being appropriate enough to indicate that his average drive is 275 yards. However, we might be able to accept a sample mean of, say, 269 yards is close enough for us to say, yes, that's true. And the way we determine that is through the use of z-scores. And that's for part C. That's what we've done this in the past, so this should be nothing new as far as calculations go. But part C says to obtain a precise criterion for deciding whether to reject the null hypothesis in favor of the alternative hypothesis. And we are going to calculate a z-score, but first we need to make some concessions here and establish a few values. So we're looking at part C, and we know that mu sub x bar and mu, we're testing to see if those are true. So we're going to say that that's 275 yards. The next thing we want to do is calculate our sigma sub x bar, the standard deviation of the sample. And remember, we find that by taking the population standard deviation divided by the square root of the sample size. I forgot to point out that in this problem, we are given a population standard deviation of 20 yards. We're going to talk more about that later in a future set of notes because we don't always know the population standard deviation. That is not an easy thing to calculate unless the population is relatively small and we can sample the entire population. So for this problem, we're just going to substitute in our 20 for the population standard deviation divided by the square root of 25, and we end up with 4 yards as our sample standard deviation. So now we can set up the equation for the z-score, and that's all part C is asking you to find is just the equation, not to compute a z-score, but just the equation. And remember, z is going to be equal to x bar minus mu sub x bar over sigma sub x bar. And we know all these values. We even know what x bar is, but we're going to leave that out. That is our variable for right now. We're just establishing the formula for z. So it's going to be x bar minus 275 over 4. And that is our formula for z. And we will use that to compute our test statistic to determine whether or not we accept or reject the null hypothesis. One other thing that we have to look at too is we know that our alpha is 0.05. That's our significance level. That was given to us in the problem right here at the 5% significance level. Alpha is 0.05. So what that means is we need to look at the z-table and we want to find the corresponding z-score that is gives us an area of 0.05. So if we go to our z-table, we've got some stuff highlighted there. We want to find 0.05 in the areas. So we have to look inside the table, and 0.05 will be somewhere between these two values right here. So I'm going to just put a little circle right there. So that's going to be negative 1.6. We scroll on up. Negative 1.6 between 0.04 and 0.05. So we would get a z-score of negative 1.645. And that is our value, that our critical value for this test statistic. So we have z is negative 1.645. For part D, we're going to apply this formula and this critical value to the sample set that we have obtained from Jaron's sample drives at the driving range with Misty. So for part D, we're going to just substitute in the sample mean into our Z value. And we get Z is equal to 264.4 minus 275 over 4. And when we simplify that, we get negative 2.65. Negative 2.65 is less than negative 1.645. And that was the claim by Misty, is that that mu would be less than the given value of 275. And in this case, we found a z-score that lies to the left of negative 1.645. Anything in this shaded region here is the rejection region. So negative 2.65 certainly falls in that rejection region. So what happens here is that we reject the null hypothesis. We are rejecting Jaron's claim that his average drive is 275 yards based on the sample data. Now, granted, there may be another time Jaron goes out. He's not as nervous around Misty, and he's popping off a couple of 300-yard drives. Who knows? And his average might be 280 yards that day. And based off that information, we could say, yeah, his average drive is probably 275 yards. But based on his performance today, we're going to have to reject the hypothesis claim that he averages 275 yards per drive. And all that is based off the z-score. Some of the terminology that we use are defined right here. The rejection region, that's whatever the shaded area is in the normal curve that leads us to reject the null hypothesis. The non-rejection region is the unshaded region. So if our z-score falls in that unshaded region, then it is a reason to not reject the null hypothesis. And then the critical value is the z-score or z-scores that separate the rejection regions and non-rejection regions. Something that's important to note is a critical value is considered part of the rejection region. So for a left-tailed test, we're looking for anything that's less than or equal to that z-score. For a right-tailed test, it's anything that's greater than or equal to. And for a two-tailed test, less than equal to and greater than equal to. And you'll see that here in a second. So here's kind of a breakdown of what are alternative hypothesis and rejection regions, how they correspond to one another. If our symbol is not equal to, it's a two-tailed test. Our rejection region lies to the left and to the right of the two z-scores respectively. If it's a left-tailed test, we use less than in our alternative hypothesis, and our rejection region lies to the left of that z-score. And then a right-tailed test is greater than, and our rejection region lies to the right of that z-score. Obtaining critical values for a one mean z test. That's what we just did in example 1, and that was the formula that we used. This is nothing that should be unfamiliar to you. But whenever we test these, we want to make sure that we're using the correct terminology and the correct formulas. So it's going to be z is equal to x bar. That's our sample mean. So we have sample mean. And then mu sub 0 or mu naught, that is the hypothesis claim from our null hypothesis. So just like in Jaron's example, it was the claim that it was 275 yards. That's why we use that. Sigma is the population standard deviation. And then n is the sample size. So for example 2, we're just gonna determine the critical values. We're going to find these corresponding z-scores at the 5% significance level. So that means that our alpha is 0.05. I'm going to do part A in a minute. I want to go ahead and do parts B and C because we already should know what those values look like. For part B, it's a left-tailed test with alpha of 0.05. If you look back at example 1, our alpha value was 0.05, it was a left-tailed test. So that means our critical value was negative 1.645. So we're going to go on down here and put negative 1.645. That is our critical value. For a right-tailed test with the same significance level, remember if it's right-tailed, we're looking at the shaded region to the right. Our z-table gives us shaded regions to the left. So we have to take 1 minus our critical value or our significance level, and we get 0.95. So we're looking for a z-score that has a shaded region of 0.95 to its left, which also happens to be the opposite of the left-tailed value, which should be 1.645. If you're not comfortable with using the symmetry of the normal curve, you can go back to the z-table and we'll find 0.95 on the z-table. We're looking for an area of positive 0.95, which should lie somewhere between these two values right here. So when we go across, we have positive 1.6. We scroll up, it's between 0.04 and 0.05. So that does in fact equal 1.645. So you can use the table or you can use the knowledge of symmetry to come up with these critical values. For the two-tailed test, we have to do this a little bit differently. And I know you probably should recall seeing this before, but the two-tailed test is where we use the z sub alpha over 2. So in our case, alpha is 0.05. And when we divide that by 2, we're going to get a z sub 0.025. So what this means is that we're looking for a z-score that has 0.025 area to its left and 1 minus 0.025 to its right, which would be 0.975. So these are our two area values that we're looking for. Again, you can apply symmetry or you can look both values up. But if we look for 0.025, let me erase this. 0.025 is in fact one of the exact values in the z-table. It lies right here. So we're going to get, that's 0.00025. I am illiterate. Okay, 0.025 would be, where am I at? Losing my mind, guys. Here we go. All right. There's 0.025. So that's negative 1.96. Symmetry would tell us then that the alternate value of that is positive 1.96. So we go back over here. Our critical values are negative 1.96 and positive 1.96. So it's these two critical values for the one mean z test at a 5% significance level. This chart right here will be helpful. We just actually used these two values right here in our calculations for example 2. Just depending on what your significance level is, if you were doing a two-tailed test, you would cut each one of these values in half. So if I wanted a significance level of z sub 0.05, I would divide that by 2, and that would lead me to the z sub 0.025. It just depends on what your significance level happens to be, but this table will be helpful. You don't have to keep going back to the z-table and looking these up every time. So the steps in the critical value approach to hypothesis testing. First, you want to state the null and alternative hypothesis. In example 1, the null hypothesis was Jaron's claim of 275-yard average. The alternative was Misty's claim that it was less than 275 yards. Then we decide on the significance level. In example 1, it was a 5% significance level, which was 0.05. We compute the value of the test statistic, which just means you find the equation for z. You don't actually calculate it, you just find the equation for z, and then you also determine what z-score is your cutoff point. And then for part 5, you would actually use the sample data, or in this case the sample mean, substitute it into your z equation, and then decide which side of the normal curve it falls on. If it's a left-tailed test, does it fall to the left of the critical value? If so, then you reject. If it falls to the right, then you do not reject. And then the same as the opposite is true if it's a right-tailed test. If it falls to the right of that score, you reject. If it falls to the left, you do not reject. And then with the two-tailed test, if it falls in between the two critical values, you do not reject. And then there's your homework. Yeah, I did this video once already, and the audio was whack, just like it was yesterday for some reason. So I'm redoing this. So we have, I'm going to look at question number 1 with you real quick. Yes, I know there's 5 parts to each one of these, but they will go quickly. Part A, determine the rejection region. So for part A, the rejection region, remember, the rejection region includes the critical value. So for part A, on number 1, we're looking at z is greater than or equal to 1.645. Part B, the non-rejection region is going to be strictly less than or strictly greater than. In this case, it's strictly less than 1.645 because the non-rejection region is everything to the left. Part C, the critical value, z is equal to 1.645. That divides our normal curve into the non-rejection and rejection regions. Part D is the significance level. This is a one-tailed test. It's a right-tailed test. So we have alpha is equal to 0.05. Now be careful on number 2, for example. It has 0.05 to the left and 0.05 to the right. So you have to add these two values together. So your alpha would be 0.1 and not 0.05. And then part E, identify it as two-tailed, left-tailed, or right-tailed. Where we're looking at the right shaded region, this is a right-tailed hypothesis test. Told you they'd go fast. So you just only have 2, 3, 4, and 5 to do. For 6, 7, and 8, determine the critical values for a one mean z test in questions 6 through 8. So a two-tailed test with alpha. Remember here you want to look at z sub alpha over 2. Here you want to look at number 7 is z is 0.05, and a left-tailed test is negative z 0.01. So it's going to be a negative z score. And then number 7 should be a positive z score. And then number 6, you should get a negative and a positive z score. So I hope that these make sense. If you guys have questions, you know how to get a hold of me. Don't hesitate to ask. And we'll just keep plugging along, and I will see you guys tomorrow in our Zoom class.